Okay, so we're looking at our first example here, and we want to determine if the series converges or diverges. First, I want to make a comment. I want to remark that notice that I'm not telling you n starts at 1 to infinity or n equals, 2 to infinity. And the reason why I'm not writing that is because if my question is does the series converge or diverge, then I don't really care where the series starts, right? If a series is going to converge, then it's going to converge regardless of where the series starts. And if a series is going to diverge, it's going to diverge regardless of where the series starts, right? So the behavior of a series in terms of convergence is determined by the long-term end behavior, not the short-term beginning behavior. Okay, so from here on out, don't be surprised if I don't give you an index for n, okay? And I'm asking if the series just converges or diverges. Now, in approaching this question, here's what we think about. We want to compare, right? We want to use the direct comparison test. So this is me, and I am trying to think, my first step is, what does this series remind me of, right? So what does this series remind you of? A reasonable answer would be to say, oh, it looks a lot like 1 over 3 to the n, right? Because you could say for large n, for large values of n, 1 over 2 plus 3 to the n is going to be really close to 1 over 3 to the n, right? Because 2 is so small compared to 3 to the n, 3 to the n is going to dominate the behavior of our fraction. So this is really good because on the right-hand side here, what we have is you got it, this is a geometric series. And can you tell if the geometric series converges or diverges? What is R? This is a geometric series, but notice we can write this as 1 over 3 to the n, 1 over 3 to the n, right? So R equals 1/3, so our series converges. So in our mind, we're thinking, the original series probably converges because the terms are so close to our convergent geometric series. Now let's see how to apply this reasoning, how to apply the direct comparison test, how to use that to confirm our suspicions. Okay, so I have written here a statement of the direct comparison test. Okay, in our mind, we're thinking that we want to be in a scenario where our conclusion is that a series converges, right? So this is what we want, just based solely on the conclusion. This is the outcome. So what should we choose for A sub n and what should we choose for B sub n? If we want our conclusion to be that our series converges, we better let A sub n equal 1 over 2 plus 3 to the n, right? And then B sub n should be equal to 1 over 3 to the n. So now what we need to verify is that 0, we've got to verify the hypotheses here, which is that 0 is less than or equal to A sub n is less than or equal to B sub n. And then we have to verify that our series with the terms B sub n converges. And then we can conclude using the direct comparison test that our original series converges to. So let's just verify. So we figured out what we want A sub n and what B sub n should be. Okay, so we said A sub n is equal to 1 over 2 plus 3 to the n. B sub n is 1 over 3 to the n. So first let's show that 0 is less than or equal to A sub n is less than or equal to B sub n for all n. Right, is this true? And yes, A sub n, the first question mark is true because each term here is greater than or equal to 0. So we'll say clearly 1 over 2 plus 3 to the n is greater than or equal to 0 for all n. And now what about b sub n? Is b sub n greater than or equal to a sub n? This is the second inequality that we need to verify. Well, we need to check, is 1 over 2 plus 3 to the n less than or equal to 1 over 3 to the n? Because we're dealing with fractions that are positive, we can cross multiply. So we're asking, is 3, right, we cross multiply, so bring that over there, bring this up here. We'll say, is 3 to the n less than or equal to 2 plus 3 to the n? And we'll say yes. So good. So essentially what we're saying is, since this denominator is larger than that denominator, the reciprocal is smaller than the reciprocal of the other one. Okay? So for our justification here, let's write and 1 over 2 plus 3 to the n is less than or equal to 1 over 3 to the n, since 3 to the n is less than or equal to 2 plus 3 to the n. Okay, so by the direct comparison test, since the sum of b sub n converges, so does the series where the terms are a sub n. Right? Now how do we know that the series of b sub n converges? We need to put in here, it is a geometric series with n equal to, with r equal to 1/3. Right? Because remember, that's kind of part of why we chose this to be our b sub n series, was because we said this is going to be a geometric series and the ratio is going to be 1/3. So the answer is that it converges, and it converges by the direct comparison test with 1 over the series with the terms 1 over 3 to the n. That's it.